All right, so let's dive into something I know you've been asking about, pile foundations. We're going deep, really deep into how these things are engineered
Yeah.
using,
Oh, this is gonna be fun.
yeah, we're looking at excerpts from the Indian Standard Code of Practice for design and construction of pile foundations.
Okay.
Specifically, Section 1 of IS.2911, Part ISEC 1, 1979, which focuses on driven cast in situ concrete piles. Now, I know that sounds like a mouthful, but trust me,
Yeah.
it's really cool. It's like peeking behind the curtain, seeing how engineers create those hidden support systems that literally hold up our buildings.
Yeah, you know what I think is fascinating about this document? It lays out this incredibly detailed process, I mean, step by step, of how you actually design and build these
Oh,
things.
wow.
From picking the right materials to making sure that those piles can withstand the pressure.
Yeah.
Literally, with load testing.
That's pretty cool.
Yeah.
So before we get, too far into the weeds here, let's start with the basics. Why do we even need pile foundations? I mean, what's the point?
Well, imagine you're trying to build something, a house, a bridge, whatever, on ground that's soft or unstable.
Right.
You need a way to transfer the weight of that structure to something, well, stronger, something more solid.
Uh-huh.
And that's where pile foundations come in. They're basically these long, sturdy columns
Right.
that reach down, down, down to those deeper, more stable layers of soil or rock.
So instead of building on shaky ground, you're essentially building on these deep, solid bases.
Exactly.
Yeah.
And there are actually a couple of different ways that these piles do their job of transferring the load. One way is they can act just like columns, directly supported by solid rock
Okay.
or really strong soil at the bottom, and we call those end-bearing piles.
Okay.
The other way is they rely on friction, basically the friction between the surface of the pile and the surrounding soil,
Oh, wow.
to kind of hold them in place, grip them, and we call those friction piles.
Interesting. So how do engineers figure out, like, which type of pile to use?
That's a great question.
Is it just, their favorite?
It's not like picking your favorite ice cream flavor,
Okay.
although that would be nice. No, it really depends a lot on what the soil is like where you're building.
That makes sense.
That's why site investigation is absolutely crucial. Like, before you even think about putting a pile in the ground.
Yeah, you wouldn't build a house without knowing, what kind of foundation you need.
Exactly. And there's actually another standard, IS.1892, 1979,
Great.
called the Code of Practice for Subsurface Investigations for Foundations.
Okay.
That tells you exactly what kind of tests you need, what kind of data you need to collect.
That's cool.
Yeah, it's like a soil detective's toolkit. You're looking at soil types, strength, how much it compresses under pressure, groundwater conditions, even checking for like chemicals that could damage the concrete.
Wow. So once you have all that information, then you can start thinking about actually building the things, right?
Yeah.
I mean, when I picture it in my head, I'm thinking like a giant hammer
Yeah.
pounding these things into the ground.
Yeah.
But I'm guessing there's more to it than that.
Oh, yeah. Yeah, definitely.
Yeah.
You're right. It's not just about hitting things hard. Um, The type of equipment you need, well, it varies a lot. Depends on what kind of pile you're using, what the soil's like, how deep you need to go.
Okay.
You've got your, drop hammers, which are basically using gravity to do the job.
Right.
And then there are these more powerful hammers for really tough jobs.
Okay.
Those use steam or compressed air.
Wow.
And to hold all this in place, you've got these massive structures called pile frames or rigs.
I mean, I guess it's like a really well choreographed dance with heavy machinery.
Oh, for sure.
So we've talked about understanding the soil and the equipment, but now let's talk about like the actual design of the piles.
Yeah.
What are some of the things engineers are thinking about when they're designing these concrete columns?
Well, one of the most important things is what we call the pile's axial capacity.
Hmm.
Think of it like the pile's backbone. It's how much weight it can handle vertically before things start to go wrong.
So axial capacity is like the pile's load-bearing limit.
Right.
Like if
Yeah.
you put too much weight on it, it's going to collapse.
Exactly. And it's not just the weight of the structure either. Piles can actually act like columns,
Mm-hmm.
and if they're not designed right, they can buckle under pressure, especially if the soil is weak.
So it's not just about sticking a strong pile in the ground. It's about making sure it can handle all the forces acting on it.
Right. And there are forces from the side too, lateral loads, we call them.
Okay.
Think wind, earthquakes, even a ship bumping into a pier, if we're talking about, a pier.
Wow. So it sounds like a physics problem waiting to happen.
Yeah, kinda. And that's where the concrete's bending strength comes in.
Okay.
So to help with that, we use reinforcement.
Reinforcement.
Yeah. Concrete's great for handling compression, but it needs a little help with tension forces, like pulling or stretching. and also with preventing cracks. So what we do is we put steel reinforcement cages inside, kind of like a skeleton,
Oh, interesting.
to give it that extra strength and flexibility.
So the steel is like the backbone of the pile, giving it that support.
Yeah.
Are there like rules for how much reinforcement you need to use?
Oh, yeah, absolutely. The Indian Standard Code has specific requirements for the minimum area of steel reinforcement you need to use in the pile shaft. It's at least 0.4% of the cross-sectional area. And depending on what you're building, the loads, the soil, that percentage can go up.
Okay, makes sense. So heavier loads, trickier soil, more reinforcement.
Right.
What about like spacing? How far apart do you need to put these things?
Good question. Spacing is really important. If you put them too close together, they can actually interfere with each other.
Really?
Yeah, and if they're too far apart, well, you might not be distributing the building's weight properly.
So it's got to be just right.
Just right.
Yeah.
Goldilocks and the three piles. A general rule of thumb is to space them at least 2.5 times the pile diameter if we're talking about end-bearing piles, and 3 times the diameter for fiction piles. And when you have a bunch of piles working together to support a structure, we call that a pile group.
Oh.
They act like a single unit, spreading the load over a wider area.
Like a team of concrete superheroes. But how do engineers know for sure that these piles can handle the job? Like, whether it's a single pile or a whole group, how do they test them?
That's where load testing comes in.
Okay.
It's like putting them through their paces.
Yeah.
You apply a controlled load to the pile and see how much it settles or moves under that pressure.
Okay, so you're basically seeing how much it gives.
Exactly. And that helps confirm that it can safely support the weight and that the foundation is really solid. And speaking of testing, there's actually a specific standard that outlines how to do load testing properly.
Oh, cool.
It's IS.2911, Part FIMI 1979.
Catchy. So now that we know how to test them, let's talk about actually building one of these driven, cast in situ concrete piles. What's the process?
Oh, this is the fun part. So first, you drive a casing into the ground. It's like a temporary mold. Then you put a reinforcement cage inside.
Oh, so it's like building the skeleton before you add the muscle.
Exactly. Then comes the concrete. Now, the concrete needs to be, well, it's got to flow easily into the casing,
Okay.
but it can't be too watery, otherwise it'll separate. Kind of like a concrete milkshake.
Okay, I get it. Smooth and consistent.
Exactly. You don't want chunks of rock and watery cement.
So you pour the concrete in, and then what? Do you just leave it?
Well, not quite. Once it's poured, you have to compact it to make sure there are no air pockets.
Okay.
And then you have to let it cure properly so it can reach its full strength. It's like baking a cake. You got to follow the recipe and give it time to bake. And one more thing, actually. When you pour the concrete, you pour it a bit higher than the cutoff level,
Oh, why is that?
because that way you can remove any weak concrete or what we call latents. It's like a weak surface layer that can form before you connect the pile cap. So you're essentially trimming the edges to make sure you have a clean, strong surface for that connection point.
It's all about making sure every part of the pile is strong.
Right. Exactly. Every little detail matters. But what happens if something goes wrong? During construction?
Oh, yeah. What if a pile is messed up somehow?
Well, luckily the code addresses that too.
Oh, good.
It has procedures for dealing with what we call defective piles.
Oh, wow.
So if a pile is defective, you either have to remove it or you can leave it in place, but you got to make sure it's not going to affect the other piles
Right.
or the whole foundation. And sometimes you might need to add extra piles to make up for that lost capacity.
So it's like a giant game of Jenga.
Mm.
You don't want to pull the wrong piece and make the whole thing collapse.
Exactly. And speaking of careful planning, it's really important to keep track of everything during construction.
Yeah.
Usually there's an inspector on site who's meticulously recording all the important details about how each pile is installed, making sure it's all done according to the design. It's like keeping a diary for each pile.
Oh, wow.
So you have a record of its whole journey from start to finish.
So they're not just building piles. They're creating a historical record of how the foundation was built.
That's one way to look at it.
That's really cool. Now, what about things like strong winds or earthquakes? How do they make sure these foundations can handle those?
That's a great question. And the Indian Standard Code actually has specific guidance for designing pile foundations to withstand these, what we call transient loads.
Okay.
So for wind loads, the code allows you to increase the safe load on a pile by a maximum of 25%.
Okay, so there's a little wiggle room there.
Right. And for earthquakes, there's another code, IS.Pot 1893, 1975.
Okay.
That's the code for earthquake-resistant design. And that's used to figure out how much you can increase the load on each pile for those kinds of events.
So it's like you're building in a safety net for those sudden gusts or tremors.
Yeah, exactly.
What happens if, during construction, a pile just doesn't quite meet that required load capacity?
Well, there's a bit of flexibility built into the code. You can actually overload a pile to a certain extent. Yeah, you can allow it to carry up to 10% more than its design capacity.
Wow.
But there are some safeguards. So the total overloading on a group of piles can't be more than 10% of the group's total capacity.
Right.
And you can't overload any single pile by more than 40% of its allowable load.
So it's like, okay, we'll give you a little bit of leeway, but you can't push it too far.
Right. It's all about maintaining that balance between safety and practicality.
It's fascinating how they think of every scenario.
Well, that's what these codes are for, to provide that guidance and make sure these structures are safe and reliable.
It really makes you appreciate how much thought goes into these things.
Yeah.
We've been talking about those downward forces,
Yeah.
but what about upward forces? Like uplift or tension?
That's a great point, and that takes us to a whole other aspect of pile design and how they behave.
Yeah, uplift forces, they can come from all sorts of things,
Yeah.
like strong winds, especially on tall buildings, or even when you have waterlogged soil, that buoyancy can create uplift. Right. So it's like the pile is caught in this tug of war between those upward and downward forces.
Exactly. And just like they have to resist being pushed down, they also have to resist being pulled up.
So how do they stay grounded when something's trying to pull them out?
Well, that's where the friction between the pile and the soil, it comes into play again. But this time it's working in the opposite direction. So instead of the soil pushing down on the pile, it's gripping onto it.
So it's like a giant hand holding onto that pile, making sure it doesn't come out.
Mm-hmm.
But how do they make sure that grip is strong enough? I mean, what if the soil's loose?
Well, the strength of that grip depends on the soil itself, how dense it is, and how much surface area of the pile is actually in contact with the soil.
Okay.
And just like with those downward forces, the design of the reinforcement cage, it's really important for resisting uplift too.
Right.
Those steel bars, they have to be anchored deep down into the soil to give it that extra grip.
It's like you're giving the pile roots.
Yeah, that's a good way to think about it.
So are there special things they do to the reinforcement when uplift is a concern?
Oh, yeah, absolutely. The length and diameter of those steel bars, even how they're arranged within the concrete, it's all carefully calculated to make sure they can handle those specific upward forces.
So it's like you're customizing the anchor system for each pile, depending on what it needs to withstand.
Exactly. And we can't forget load testing here too. We do tests to make sure the piles can handle both compression, that pushing down, and tension, that pulling up.
Oh, wow. So you actually test for both.
Yeah, we apply a controlled upward force and make sure the pile doesn't just pop out of the ground.
So it's like a reverse bungee jump.
Yeah, something like that. But, we've talked about these downward and upward forces, but we haven't really touched on those sideways pressures, those lateral loads.
Oh, yeah, right. How do those forces affect the design?
Well, lateral loads, they're super important to consider, and they can come from a lot of different sources, like strong winds, obviously,
Right.
earthquakes, even just the pressure of the soil itself pushing against, say, a retaining wall.
So it's not just about the weight of the building itself. It's about all these other forces that can push and pull on it from all sides.
Exactly. And those lateral loads, they're not all the same either. They can be big, they can be small, they can come from different directions. And how they're applied to the pile, that matters too.
Wow, okay. So how do they make sense of all of that? How do they design piles that can handle everything?
Well, this is where we start talking about soil structure interaction. It gets a little complicated.
Okay.
But the basic idea is when you have a lateral load on a pile, it's not just the pile itself resisting that force. The soil around it is helping too.
So it's like a team effort, the pile and the soil working together.
Exactly. Imagine you're pushing against a tree trunk.
Okay.
The trunk itself is going to resist, right? But the soil around the roots is also helping to keep it from moving. It's the same with piles.
So the soil acts like a giant brace, holding that pile steady.
Yeah, that's a good way to picture it.
But how do they, measure that support? I mean, how do they incorporate that into their calculations?
Well, they use what we call the modulus of subgrade reaction.
Modulus of what?
Yeah, it's a mouthful.
Yeah.
But basically, think about pushing against a mattress compared to pushing against a concrete floor.
Okay, yeah.
The concrete is way stiffer.
Right.
So it pushes back harder. That's what this modulus measures, how stiff the soil is, how much it resists moving.
Okay, I get it. So a higher modulus means the soil is more supportive. Right. It can handle those heavier loads.
Exactly. And engineers figure out this modulus by doing soil tests, looking at things like density and shear strength.
So they're basically taking the soil's pulse, seeing how strong and healthy it is.
That's a good way to put it.
So once they have that information, how do they use it?
Well, they use that modulus, along with the pile's demands, what it's made of, to calculate how much that pile is going to deflect, bend or move under those expected loads. The goal is to keep that deflection within acceptable limits. You don't want the building tipping over.
So they're basically predicting how much the pile's going to wiggle under pressure.
Yeah.
And making sure that wiggle doesn't make the building fall over.
Exactly.
But it's not just about the soil, right?
Right.
I mean, the pile itself needs to be strong enough, too.
Oh, absolutely. The material, how big it is, the reinforcement, it all matters.
Right.
So a bigger pile with more reinforcement, it's going to be stiffer, stronger.
Makes sense. So it's finding that balance between the strength of the pile and how much support it's getting from the soil.
Exactly. It's a dance between engineering and nature. But we've been talking about individual piles. What happens when you have a whole group of them working together?
Oh, yeah, good point. Does that change things?
Oh, yeah. It gets more complicated when you have multiple piles connected together, by a cap or a beam. That's what we call a pile group. And how they behave under lateral loads, well, it's not just adding up their individual strengths.
Right. Because they're all connected.
Yeah, they're interacting with each other through that connection. So it's more like a team of athletes working together.
Oh.
We have to analyze how that load is shared, how much each pile bends, how they move together. It's pretty complex.
So are there any general rules for how these groups behave?
One of the most important things is how stiff the pile cap is. A really stiff cap is going to distribute that load more evenly across all the piles.
Okay.
But if it's more flexible, well, some tiles might deflect more than others. And the spacing and arrangement of those piles, that matters too.
So it's like a choreographed dance, but with concrete. Do they test these groups too?
Oh, yeah, we do load tests on entire pile groups to make sure they can handle those lateral forces as a team. It's like putting the whole team through a workout. But, we've been talking about all the technical stuff, the forces, the materials, the calculations. But what about the bigger picture? What's the impact of all of this?
Yeah, good point. What's the societal impact of these, hidden heroes beneath our feet?
That's a great question. I mean, pile foundations, they're a big part of why we can build the things we build. They make modern life possible. Think about skyscrapers, bridges, harbors, those offshore wind farms.
Oh, wow. Yeah.
They all rely on strong foundations, and a lot of the time that means piles.
It's like they're the roots of our civilization, holding everything up.
Exactly. Without them, well, our world would look a lot different. We wouldn't be able to build as high, as strong. They allow us to push those boundaries.
So they're not just supporting buildings, they're supporting our dreams.
That's a beautiful way to put it. They're a symbol of what we can achieve when we use science and engineering to solve problems.
Yeah.
And as we face challenges like climate change, growing cities, they're going to become even more important.
Right, because we need more resilient infrastructure. We need buildings that can last.
Exactly. So next time you see a skyscraper or you drive over a bridge, take a moment to think about what's holding it all up. It might be piles working silently down below, making it all possible.
Yeah, it's really amazing when you think about it. And it's not just the structures themselves, it's the people who design and build them. It's pretty cool.
Yeah.
But, we've talked a lot about pile foundations on land.
Yeah.
What about those built in the ocean? How are they different?
Oh, marine pile foundations, that's a whole other world.
Yeah.
It's a lot more challenging. You have to understand not just the soil, but the ocean itself.
Right.
The waves, the currents, the tides.
So it's like taking everything we've talked about and adding a whole new layer of complexity.
Exactly. And one of the biggest challenges is corrosion.
Corrosion.
Yeah, seawater is really corrosive.
Oh, right, of course.
It can eat away at the concrete, the steel. So you have to design for that. You have to use special materials, coatings, even systems that protect against corrosion.
Yeah.
It's like giving those piles a diving suit.
Okay, I get it. So what else is different about building in the ocean?
Well, the ocean is constantly moving.
Right.
You have waves, currents, tides, and all those things exert forces on the piles. They can sway, vibrate, even fatigue over time.
So you're not just dealing with, like, a static load.
Right.
It's constantly changing.
Right. So engineers, they use all sorts of fancy models to try and predict those forces. and then they design the piles to handle them.
So you have to give them sea legs, basically.
Yeah, exactly. And the construction process itself, it's completely different. You need special equipment, divers, barges, cranes,
So you're basically taking a construction site and putting it underwater.
pretty much. And even pouring the concrete is different.
Oh, wow. How do they do that?
They often use this technique called tremi-concreting.
Tree.
Yeah, it's where you pour the concrete through a pipe that goes all the way down to the bottom of the excavation,
Okay.
so it doesn't mix with the seawater.
So it's like a giant concrete milkshake.
Yeah, something like that.
You're pouring it through a straw.
Exactly. And even after the piles are in, they often need extra protection. Things like rock armor or scour protection systems to keep those currents and waves from eroding the soil around them.
So it's like they're wearing armor.
Yeah, they have to be tough to survive in the ocean. But it's really remarkable how we've been able to take those same basic principles of pile foundations and adapt them to this really challenging environment.
Yeah, it shows you how far we can push things, right?
Absolutely. And as we look to the future, with all this interest in offshore wind energy, aquaculture, I think we're going to see even more innovation in this area.
Right, because we're going to need those foundations to support all those new structures. It's exciting to think about what we might come up with.
Yeah, it is. And we can learn a lot from nature, too.
Oh, how so?
Well, marine organisms, they've evolved some incredible ways of surviving in that constantly changing environment.
Right.
And we can learn from that, use those ideas to design and build even better structures. It's like nature's blueprint for resilience.
Yeah, that's a great point. We talked a lot about the technical stuff, but we haven't really touched on the human side of things. What's it like for the engineers who work on these projects?
Oh, it's a challenging but rewarding field. You're constantly solving problems, pushing the boundaries, and there's a real sense of accomplishment when you see something you've designed come to life.
Right, because you're building something that's going to last, that's going to make a difference.
Exactly. And it's a collaborative effort. We work with architects, contractors, other specialists. It's like a big team. And when those structures stand tall, knowing you were part of that, it's a great feeling. It's why we do what we do.
It's like you're leaving your mark on the world.
In a way, yeah. And it's not always glamorous. It can be tough, but it's definitely rewarding.
So what would you say to someone who's interested in a career in foundation engineering? What advice would you give them?
Oh, I'd say go for it.
Yeah.
It's a challenging and rewarding field, and there's a lot of opportunity, but you got to be prepared to work hard, to learn constantly, and to embrace the unexpected, because every project is different. But if you're up for the challenge, it's a great field to be in.
So what are some of the things that people can do to, get started?
Well, get a good education. Study civil engineering, geotechnical engineering.
Okay.
Get involved in research, internships.
Right.
Learn from experienced engineers. And never stop learning.
Because the field's always changing.
Oh, absolutely. That's one of the things that makes it so exciting.
So we've covered a lot of ground here, literally and figuratively. Any final thoughts you want to leave our listeners with?
Well, just that pile foundations, they're all around us.
Right.
They're the unsung heroes of the built environment.
Holding everything up.
Exactly. So next time you walk across a bridge or you're in a skyscraper, just take a moment to appreciate what's going on down below, holding it all up. It's pretty amazing.
It is. It's the foundation of our world.
It really is amazing.
Yeah.
How these hidden structures down there in the ground, they've let us build these incredible things, skyscrapers, bridges, even whole harbors.
Yeah, it's pretty mind-blowing when you think about it. All that's going on beneath the surface just to hold up the world we see. We've talked about, piles as individual units and as teams. But are there ever times when they're used with, other types of foundations, like a combo approach?
Oh, that's a great question. And it really shows how versatile pile foundations are. There are definitely situations where we use piles along with other types of foundations to create what we call a composite system. So you're getting the best of both worlds.
So it's like building the ultimate foundation team.
Yeah.
Choosing the right players for each position.
Yeah, exactly. Imagine you have a building where part of it's on solid rock, no problem.
Okay.
But another part needs to reach deeper for that stable soil.
Right.
Well, you might use piles for that section, while the other part can sit on a more traditional foundation.
So each foundation type is doing what it does best.
Right. Like a division of labor.
Another common thing we see is using piles together with those shallower foundations.
Oh yeah, like strip footings or raft foundations. Those piles might be supporting the really heavy stuff like columns or walls,
Okay.
while the shallow foundation takes care of the rest.
It's like having the heavy lifters and the all-around players all on the same team.
Yeah, I like that. And sometimes we even use piles along with ground improvement techniques.
Oh, what's that?
Well, sometimes the soil's just not strong enough to support those piles directly.
Okay.
So we might do things like compact the soil or inject grout to make it stronger, and then we can install the piles.
So it's like giving the soil a workout, making it more buff.
Yeah, exactly. So it can team up with those piles and create a really solid base. And all of these combinations, they show how much creative problem solving goes into foundation engineering. It's not just one size fits all.
Right. You have to figure out what works best for each specific project. It sounds pretty challenging, but also really interesting. What would you say is like the most rewarding part of foundation engineering?
Hmm. For me, it's knowing that I'm helping to build the foundations for the things that, well, that shape our lives.
Right.
It's about using science and engineering to solve real-world problems and create something that's going to last for, I mean, hopefully for centuries.
Like you're leaving behind a legacy.
Yeah, a legacy of stability.
I like that.
It's a good feeling. And there's also the intellectual challenge. Foundation engineering is always changing.
Right.
There are new technologies, new materials, new ways of thinking about things. So you're always learning, always pushing the boundaries. That keeps things interesting.
Yeah, you're never bored. Right.
Exactly. And I can't forget the people I get to work with. We collaborate with architects, contractors, all sorts of experts. It's a real team effort. We're all working together to make these complex projects a reality. And when it all comes together, when you see that structure standing there knowing you were part of that, it's a pretty amazing feeling.
Yeah, it must be. It's like creating something that's bigger than yourself. It's really cool. Well, we've covered a lot of ground today. Any final thoughts you'd like to share with our listeners?
Just that, pile foundations, they're everywhere. They're literally the foundation of our modern world. So next time you see a bridge or a tall building, take a moment to think about what's holding it all up.
Think about those piles down below, working hard, silently.
Exactly. They're the unsung heroes of our built environment. And without them, our world would be a very different place.
That's a great point. It's something we often take for granted, but it's really amazing when you stop and think about it. Well, this has been a fantastic deep dive. I've learned a lot, and I hope our listeners have too.
I've enjoyed it.
Thanks so much for joining us today and sharing your expertise.
My pleasure.
And to our listeners, thank you for tuning in. We hope you've enjoyed this exploration into the fascinating world of pile foundations. Until next time, keep exploring, keep learning, and keep building.